Okay, so the first function is x plus 3 times x minus 2, and the other function is x minus 2. So it looks like there we go. This is g of x, and this is f of x. Where do the graphs intersect on the x-axis? Yeah, they intersect at x equals 2. All right, very good. So the next step, find the roots of f of x. Well, let's see. X plus 3, set that equal to 0 and solve. We'll have a root at negative 3. And set this equal to 0 and solve. We'll have a root at positive 2. And in fact, those are the two x-intercepts. So that's that one. And that's that one. And then for g of x, the root is at positive 2. Okay. So far, yes. Okay, well, let's go to the next step. The next step says graph y equals x plus 3x minus 2 divided by x minus 2. So let's put that in our calculator and make a graph. So I'm going to get rid of that. X plus 3, x minus 2 divided by x minus 2. And it looks like we have an x-intercept at negative 3 and a y-intercept at 3. So there's the function. And the next step says use the trace function on your calculator to determine the y value at the x-axis intersection point from above. Well, the x-axis intersection point from above was x equals 2. So what we can do is press the trace button, press 2, enter to get the y value. And it's undefined. Excellent. So y equals undefined. But when you look at this graph, there's no vertical asymptote there, which is what we had before. It looks like it works. So I guess, why are we getting an undefined at x equals 2? Any idea? Yes. Yeah, that's exactly it. So what we have is, in the denominator, if you plug in a root of 2, then we divide by 0. So why do we have an undefined? Because we divide by 0. But what's interesting is that we have the same term in the numerator. And if we were to simplify this function, wouldn't the x minus 2 in the numerator and denominator cancel? And we would be left with x plus 3. What do you suppose that graph looks like? Yeah, it looks exactly like this. What do you notice? They are the same except, well, here's what we know, right? Y-intercept of 3 and a slope of 1, so up 1 over 1, up 1 over 1. So they look the same, but there's one difference. When we have the x minus 2 over x minus 2, we're undefined at x equals 2. Whereas if you plug a 2 into this equation, isn't 2 plus 3 5? Yeah. So it exists for this, but not for the rational function. And so what's going on is that when we have this term divided by a term that cancels out, at x equals 2, there's a little tiny hole in the straight line where the function doesn't exist. Because if you plug in x equals 2, it's undefined. But if you were to go on either side of this, say for example you put in 2.00001, well that would exist because you're not dividing by 0. Or if you did 1.99999, that would exist because you're not dividing by 0. So on either side of x equals 2, you get this straight line, but at x equals 2, you have a divide by 0, and you get a little hole there. That's called a removable discontinuity, or a hole. It's like a discontinuity in the space-time continuum. Yeah. So, this function and the rational function, they are the same except for the hole. Now, last thing. Compare the x-intercept with the roots of the numerator. Well, our x-intercept is -3. When you look at the roots of the numerator, the roots are -3 and +2. The +2 root cancels with the +2 on the bottom, and so the only x-intercept comes from the non-canceling root in the numerator. So what do we notice? The x-intercept is the same as the non-canceled out root in the numerator. Anybody remember the movie Diary of a Wimpy Kid? And there's the one kid that always dresses the same as the other kid to drive him nuts. You don't remember that? They called them matchers. Yeah. One person remembers. You all remember the cheese touch, though, right? Yeah, the cheese touch. Well, there was the one kid, and then there was the other goofy kid that always dressed the same and drove them nuts. They called them matchers. Well, in a sense, that's what we have right here. We have a matcher, top and bottom. And so if you have a matcher, top and bottom, you end up with a hole. Okay? All right, if you flip the page, what you're going to notice is that this first section is exactly the same as page 1. So there's no need to repeat that. Let's go straight to this next portion. Graph this function on your calculator and draw a sketch. But before we do, based on what we did in Exploration 1, can you make any predictions? For example, do you see any matchers? There's a matcher right there. What's the root of the matcher? What's the root of the numerator? 2, and the root of this part of the denominator is a 2. It matches. What do you predict is going to happen at x equals 2? A whole, yeah. And then, if those canceled out and we just had 1 over x plus 3, what do you think would happen at this root here? And by the way, what is this root? -3. What do you predict will happen there? Well, if you plug in -3, -3 plus 3 is 0. What happens if you have 1 divided by 0? It's undefined, and what do you expect will happen? Well, let's find out. Let's find out. What I would expect, I think we learned on Thursday what will happen there. Okay, so x minus 2 divided by double parentheses x plus 3, x minus 2. And there is the function. So I'm going to press the trace button, and I'm going to plug in the root of the matcher, which is 2, so 2, enter, and y is undefined. So at x equals 2, y is undefined, and because we divide by 0, we're going to get a whole, because it's the same top and bottom. Now, at -3, if you do -3 enter, y is also undefined. What's going on there? Vertical asymptote. So, vertical asymptote there. The function looks like this in quadrant 3, and then it comes down and it crosses the y-axis, and when it gets to x equals 2, there's a little tiny hole, and then after that it continues on. So, there's the hole at x equals 2. Their vertical asymptote at x equals -3. If we simplify this function, the x minus 2 cancels, and so we're left with x plus 3 in the denominator. What's in the numerator? A 1. If we were to graph 1 over x plus 3, what do you think this would look like compared to the graph of the complete function? It would be the same except for the whole. And the vertical asymptote has the same root as the non-canceled root in the denominator. Let's flip the page over, do one more. Alright, so we have two functions, f of x, g of x. Let's graph those two and see what it looks like. X plus 1, x minus 1, x minus 4, x minus 2, x minus 4, x minus 6. So there's the first function, f of x. And g of x. So f of x, g of x. Pretty fun looking graph. Where do the two graphs intersect on the x-axis? Yeah, right there at x equals 4. Alright, let's find the roots of f of x, which are -1, +1, and +4, and the roots of g of x are 2, 4, and 6. And there's our two matching roots. And if we come down to this next rational function, you'll notice that's the same equations as above. We have f of x in the numerator and g of x in the denominator. And what do you notice right there? Yeah, they're matchers. Do you have a prediction about what will happen on the graph at that location of 4? Predict a hole. Okay, cool. What do you think will happen at the non-canceling roots in the numerator at -1 and +1? What do you think will happen there? Numerator. X-intercepts maybe? And then what do you think will happen at the non-canceling roots of the denominator? Yeah, let's see, that's 2 and 6. Yeah, probably a vertical asymptote. Well, let's graph that and see if our prediction is true. So divided by double parenthesis x minus 2, x minus 4, x minus 6. There's the graph. So let's test out our theory. Press the trace. Let's check the hole first. If you do 4, enter, y is undefined. And so that works. Let's try the x-intercepts. -1, enter. Yeah, that gives us y0. +1, enter, gives us y0. So those two are x-intercepts. If you do 2, enter, we get y is undefined. And so that gives us a vertical asymptote. And the other non-canceling root in the denominator is 6, and that's undefined. So that's a vertical asymptote. So we know the function looks like this. As the function comes up here, when it reaches x equals 4, it becomes undefined in a hole, and then continues on, and then does something like that. If we were to simplify our rational functions, the x minus 4s would cancel, and we'd be left with x plus 1, x minus 1, and x minus 2, and x minus 6. And what do you think? If we graphed this, what do you predict it would look like compared to our sketch right here? Same, except for the hole. And the x-intercepts are the roots of the non-canceled numerator, and the vertical asymptotes are the roots of the non-canceled denominator. I'm not going to write that out because we've talked about that. Okay. Let's finish up on the back page. And we have this function f of x, which is x minus a, x plus b, x minus c, and g of x, which is x minus a, x plus b, x minus d, where a, b, c, and d are positive real numbers, and a does not equal b, does not equal c, does not equal d. Now this looks different because it has all letters instead of variables and numbers. But you can imagine that a, b, c, and d are just numbers like 1, 2, 3, and 4. We've just called them letters. Okay. Let's look at this function. I see a matcher, x minus a over x minus a. What is the root of x minus a? Yeah, it'd be positive a. Because remember, we just take whatever that number is and it's an opposite sign. And because it's a matcher, what do you think is going to happen at a? Yeah, predict a hole. Okay. Now, next we have x plus b over x plus b. That's also a matcher. What is the root? Negative b. Very good. And what do you predict will happen there? A hole. Yeah. There are no more matchers. Let's look at this x minus c. What is the root? Positive c. What do you think is going to happen there? An x-intercept. Yep. And in the denominator we have x minus d. The root would be negative d and a vertical asymptote. Positive d. Yeah, right. Sorry about that. Thank you for catching me. Okay, so where are the removable discontinuities? At x equals a and negative b. Now this says where are the roots. This really should say x-intercepts. Where are the x-intercepts? At x equals c. And where are the vertical asymptotes? X equals d. Nice. All right. What is a good procedure to follow when analyzing and graphing any rational function? That means finding the domain, the roots, and discontinuities. Well, here's what I recommend. Step number 1, factor the numerator and the denominator, because you can't find the roots easily unless you have the polynomial in factored form. Step number 2, look for duplicated zeros in the numerator and denominator. Look for the matchers first, because those will give you the wholes. Then look for zeros in the numerator. Those will give you the X-intercepts. Then look for zeros in the denominator. That'll give you the vertical asymptotes. And then lastly is the domain. The domain is all of the x values that work in the equation. So any value of x that you can plug into the equation that gives you a y value is in the domain. And so what we say is the domain is all real numbers except zeros that cause wholes and vertical asymptotes, because those are the only places where the function doesn't exist. Okay?